So as Paul's already said, the subject tonight is the age of the earth. And we're going to look at some of the evidence for a young earth. And we're going to cover quite a lot of different topics. We're going to start with a bit of biology. We're going to do a bit of astronomy. We're going to do some chemistry. We're going to look at history, ancient history. And we're going to look at geology. Of course, you can't address the question of the age of the earth without looking at geology. We'll save the best to last. Before we start, though, why are we actually talking about this subject? Why is there a debate about the age of the earth? Well, for a Christian, the debate arises because of what we read in the Bible. And here's Genesis chapter 1, verse 5. And we read here, in the creation account in Genesis chapter 1, God called the light day, and the darkness he called night. And there was an evening, there was a morning, the first day. And that's the end of the first day of creation as recorded in Genesis. And there are a number of days of creation, as you know, 6 days of creation recorded in Genesis. And this phrase reappears every time. And there's another mention of the word day in Genesis 1, chapter 14, talking about God saying, "Let there be lights in the expanse of the heavens to separate the day from the night, and let them be for signs and for seasons, for days and years." So we have an idea of time in the first chapter of the book of the Bible. And what we need to know is what do these days mean? Because if the current scientific theories are correct, the Earth is actually billions of years old, and life evolved over a long period of time, and it's not something that happened on a number of days, 6 days, as the Bible says. But maybe we don't understand correctly what the Bible is saying. Maybe there's some misunderstanding in the word day. Well, I want to quote to you a Professor Barr, who was Regius Professor of Hebrew at Oxford University. He's now retired, but he wrote in reply to a question sent to him by somebody who was researching this subject and wanted to know, what did actually the text of the Bible say? Does it actually say days of 24 hours, or is it more open to different interpretations? And this is what he said. The writers of Genesis intended to convey to their readers the idea that creation took place in a series of 6 days, which were the same as the days of 24 hours that we now experience. So he's actually saying, well, by the way, all these efforts of various people who are trying to say, well, actually, it's not days of 24 hours, their efforts are kind of stillborn, because as far as the text is concerned, as far as the language is concerned, as far as the Hebrew language is concerned, it means 6 days or 24 hours. Interestingly, Professor Barr then goes on to say, but we now know that's not true. So although he admits that's what it says, he says, I don't believe it, because science has told me that the Earth is actually billions of years old, therefore it can't be true. But that's what it says. Or you can take the alternative approach, which is one I take, is that, well, if that's what God said, maybe we should take it quite seriously. But then we are confronted, of course, with the scientific counter-argument. So let's look at some of the science. As a scientist who is also a Christian, I'm not afraid to look at the science, so we start looking at the science. Let's look at biology to start with. A couple of pieces of evidence from biology which support the idea that the Earth actually might be quite young. We can look at human population growth, and we're also going to look at human skeletons. We're not actually going to look at human skeletons, we're going to think about human skeletons and human tombs. Growth rates first, though. Human population growth. It's an interesting question to ask is, how long would it take for this Earth to have 6 billion people on it? We now have 6 billion people on this Earth. Would that take a long time? Would that take a short time? How long would it actually take? Well, present population, as I've already said, is 6 billion, and the present growth rate over recent years is about 2% per year, an increase of about 2% per year. It might actually be slowing down now, but that's a fairly slow growth rate. But if that growth rate, say, has been constant over a period of time, how long would it take if we started with 2 people to get to 6 million people? Anybody fancy a guess? Come on, be brave. 6,000 years. Too long. It's actually only about 1,100 years to get from 2 people to 6 billion at a growth rate of 2%. And that's a fairly modest growth rate. So actually there's plenty of time to reach the population of the Earth, starting just from 2 people, and that's not a problem from that point of view. The question really we have to ask is why the humanity has not filled the Earth a lot quicker than we currently have, if we've been on this planet for The conservative estimates would say that human beings have been around, if you're an evolutionist, for about 100,000 years. So why have we not already filled the planet several times over? Maybe because we haven't been around that long to fill the planet several times over. And just to kind of support that argument, let's think about human skeletons. From time to time, archaeologists and paleontologists dig up a human skeleton, a human fossil, or a fossil that might be quite human-like. It'd be interesting to think about, well, how many should there be? Now, we're told, according to the evolutionists again, that Stone Age lasted about 100,000 years. Okay, just taking the evolutionary side of the argument. So the question is, where are all the bodies? Because if you had a population of about 1 to 10 million individuals, which is not very many, it's a fairly conservative estimate, living on this planet for about 100,000 years, you can actually work out how many dead bodies there should be around, how many graves you would find. Now, assuming also that human beings, one of the features of humanity is that we tend to bury our dead rather than just dispose of them in the dustbin. So you find graves and you find artifacts. So taking those assumptions, actually, the maths comes out with about 4 billion people would have died in that 100,000 years. So the question is, where are all the tombs? Because if you actually work it out, if you start calculating the surface area of the land on this planet, you will find that if you take Europe, Asia, Africa, North and South America, you end up with a density of about 80 bodies per square mile. So you'd expect to find tombs of 80 people in every square mile of land surface on this planet, if these numbers are correct. So the question is, where are they all? Well, maybe there weren't that many people for that long period of time. So two pieces of evidence from biology which suggest actually that the Earth could be a lot younger than we're told. Some of these numbers don't add up. Somewhere something's wrong. Now let's move to astronomy. I'm a bit of an amateur astronomer. I have my telescope. I get it out from time to time. I was out the other night looking at Saturn, enjoying the view. But astronomy is an interesting subject. And we're going to look at this, think about solar eclipses. We're going to think about comets. We're going to have a look at what's called the faint sun paradox. All of these three things actually suggest that the standard story about the Earth being billions of years old doesn't quite work. Solar eclipses. The moon, as you no doubt know, is 400 times smaller than the sun. It also happens to be 400 times closer to us than the sun is when it's between the Earth and the sun, because on it's the other side, it's a bit further away. But when the moon passes between the Earth and the sun, or is between the Earth and the sun, it's actually 400 times closer. 400 times smaller, 400 times closer. So it actually has the same apparent diameter, which gives you a total solar eclipse. And the other thing about the moon is it's actually receding from the Earth. It's getting further away. So in about 20 or 30 million years, we won't be able to observe these amazing phenomena of a total solar eclipse. So you might say, well, so what? Well, hang on, let's think about this. 20 to 30 million years, geologically speaking, when you're talking about billions, that's nothing. Okay? We just happen to be here to observe a total solar eclipse when it happens to be occurring. 20 million years either way, we'd either be too early or too late on the scene. And as I say, when you're talking about billions of years of evolution, why do we actually happen to be here at this particular time? Just coincidence that we see solar eclipses. And not to forget also that the fact that the moon is the right size in the right place relative to the sun and the Earth actually cause a solar eclipse to occur. So many people think there's rather too many coincidences. I tend to think that's rather too many coincidences. So maybe we're on this Earth at this time to observe a solar eclipse because God meant us to be here to observe solar eclipses. And in fact, the universe is quite young and we've always been able to observe a solar eclipse throughout the whole history of the Earth. Could somebody get me a glass of water, please? Thank you. So solar eclipses are a rather interesting phenomenon and do suggest that maybe we're here at the right geological epoch, which is a rather amazing coincidence if the Earth is billions of years old. Comets. Comets are very interesting objects. I don't know whether any of you observed the recent comet that was actually visible from the skies of Edinburgh last year, October time. If you had a pair of binoculars, you could actually see it from Edinburgh. If you were outside of Edinburgh and you didn't have light pollution, you could actually see it with the naked eye. Well, long-period comets are very strange objects. According to the standard theories, the comets were formed about the same time as the planets, which if you're an evolutionist or you're an evolutionary cosmologist, would put the formation of the comets at about 4.5 billion years ago. But comets, as you know, have a tail, and here's a picture of Hale-Bopp, have a tail because as they get nearer the sun, they warm up and they start to lose material into space, which is then illuminated by the sun, which gives you the tail, which is very spectacular. So the average life of a comet is only several thousand years, depending how often it comes past the sun. Something like Halley's Comet comes every 80 or so years, but after a while, it's going to actually all boil away and have nothing left. So the average life of a long-period comet, not the short-period comets, there's another family of comets called the short-period comets that go around very quickly in a couple of years, rather than long-period comets which go around maybe tens of to 100 years. The average life is only going to be about 1,000 years. So you need to have a source of these comets if they were actually formed billions of years ago and are still being used up. Otherwise, you run out very quickly. And so the astronomers have got around the problem. Well, an astronomer by the name of Oort got around the problem by saying, well, actually, he suggested the Oort cloud as a source of the long-period comets. So what is the Oort cloud? Well, Mr. Oort made his suggestion back in 1950. We have a diagram of what he thinks the Oort cloud looks like. So you have the planets in the middle here, and Pluto is out here. And out to about 1 light year, you have what's called the Oort cloud. It's basically a cloud of comet-sized objects in a spherical shell around the sun. And every now and then, a passing star just perturbs the gravitational field slightly, and one of these comets drops in towards the sun. So they can come from any direction, which is what long-period comets do. Long-period comets are interesting because they can come actually from out 90 degrees perpendicular to the Earth, or they can come in the same plane as planets. So they can come from any direction, which means you need, if you have a 4 billion year old solar system, you need a constant source of these comets because they only last for a few thousand years maximum. So Mr. Jan Oort, who's a Dutchman, I believe, suggested this Oort cloud in the 1950s. And he suggested this cloud, but it's never actually been observed. It's a very interesting phenomenon, and some astronomers have made a comment in the scientific literature that here we have an object that's never been observed, or a phenomenon that's never been observed, which is cited in the literature over and over again to explain the origin of comets. So is that scientific? Well, not very. So, but to get around the problem of where the comets come from, we have to have this cloud out there. It's a reasonable assumption, but it's only an assumption. And you might recently have heard of some objects which they think came from the Oort cloud. There's one called Sedna, which people think might be an Oort cloud object. Unfortunately, it's rather large, and it's actually too close. It's actually only about, just maybe twice the distance of Pluto from the Sun, so it's not far enough out to be one of the Oort cloud comets. It's actually too big. It's several hundred kilometers across. It's almost planet size, so it's very unlikely to actually be an Oort cloud object. So the best piece of evidence they've got is this object, which is not really the right size, it's not really in the right place. So we have a problem if you have an old solar system. Where do all the comets come from? And the alternative hypothesis is, well, actually, the comets aren't that old, so therefore there's still plenty of them left to go around the sun and give us these interesting astronomical displays. Another problem for the old cosmos argument, or the old Earth argument, is the faint sun paradox. Now, if the sun is a main sequence star, which most people accept that it is, don't have much problem with that, a main sequence star has a lifetime, on conventional terms, of 10 billion years. This is the astronomical accepted theory. So the sun is going to last for about another 5 billion years, so don't worry too much. So it's about 4.5 to 5 billion years old, if the evolutionary story is correct. Which means about half the hydrogen in the sun is now being used up and it's been converted into helium, which gives us the energy, which keeps us warm, gives us light, and brings life on the Earth. Without that, we'd be nowhere. So about half the hydrogen is used up. And as the hydrogen is used up, it actually gets hotter rather than colder, surprisingly enough. There's no problem there. It's basically because of the physics of the sun. Don't ask me to go into it, I'm a biologist, but that's the accepted theory. Nobody questions that. But that means that if the sun has evolved and it was now nearly 40% brighter than it would have been 4.5 billion years ago, which means basically 40% hotter. Now, we think we've got a problem with global warming now. That's nothing. 40% increase in brightness, I mean, we'd be fried. But if the Earth is 4.5 billion years old, the Earth would have been a block of ice, more than a block of ice. It would have been freezing cold. There would be no possibility of life, the kind of life we have on Earth now. So the geologists come up with various scenarios, say, well, we had lots of greenhouse gases to keep the Earth warm. Well, some of them have said, well, we did have kind of a snowball Earth kind of situation. But these are kind of ad hoc justifications to try and explain how life could possibly evolve while the Earth was a block of ice, because the sun was a good deal colder than it is now. And to get around the problem, you actually have to have the atmosphere evolving at the same rate the sun is evolving and life is evolving, so it all fits together. Which, if you ask me, is quite a big ask. An awful lot of coincidences has to take place for that to occur. Whereas if the sun is actually only 6,000 years old, the problem disappears. So the faint sun paradox is a big issue for evolutionists, and they haven't really got a convincing argument to explain how life could have evolved when the sun was an awful lot cooler than it is now. So enough of astronomy. Let's do a bit of chemistry. Two bits of evidence which suggest that the Earth is actually a lot younger than we're told. One coming from salt in the oceans, and the other from helium in the atmosphere. Right, the salt in the oceans comes mainly from rivers. Rivers will wash over the rocks, the soil, and salt that's present in the rocks, in the soil, is dissolved in the river and taken out to sea, and it gradually accumulates. So there's a rate of input of salt into the seas, which can be measured. And the rate of input is actually worldwide 450 million tons of sodium, in terms of sodium, per year. Salt is sodium chloride. So that's easy to measure, and there's nobody contests the numbers here, actually. The rate of loss is about 120 million tons per year, most of the loss being that basically as the sea washes up on the shore, you get spray, and the salt is deposited on your car and makes it rust. That's why your cars rust when you live in Edinburgh. So the rate of loss is actually fairly easy to measure. It's about 120 million tons per year. So you can actually work out from knowing the rates of input and the rates of output as how long it would take for the sea to be at its present salinity starting from zero, which is your most favourable assumption for the evolutionist. So if we make the assumption that to start off with all the sea was fresh water, it would actually only take 40 to 60 million years for the present concentration to be reached. And this is a maximum figure, okay? This is the maximum age of the sea based on the amount of salt that there is in it, taking into account all the figures that we know. So where's your billions of years? So somehow you've got to explain away the fact that the sea is not an awful lot saltier than it is. So again, suggesting that the sea might possibly be a good deal younger than 3 billion years. Helium in the atmosphere is another piece of evidence which suggests, again, that the Earth is a lot younger, or the Earth's atmosphere, and therefore the Earth, is a lot younger than we're led to believe sometimes. Most of the helium in the Earth's atmosphere comes from radioactive decay. Helium is a small molecule, 2 protons, 2 neutrons, and a couple of electrons, variable, doesn't have to have electrons. But helium is quite a small molecule. But the main source, as far as we can tell, is from radioactive decay. And we're going to come back to helium and radioactive decay towards the end of this talk. And the helium, of course, being a light molecule, is constantly lost from the Earth's atmosphere into space. It's not very difficult for it to leave. So people have looked at the helium balance in the atmosphere, and they've discovered that the rate at which helium enters the atmosphere vastly outweighs the rate that it's lost into space. So an awful lot more helium is going into the atmosphere than is currently being lost. Right, so there's a big imbalance. It's huge. And what it basically means is that the current quantity of helium would accumulate in no more than 2 million years. Again, the maximum age of the atmosphere based on the helium balance, the inputs and outputs, is 2 million years. That's all you've got. So you need to explain why the atmosphere appears to be so young if you're an evolutionist and you believe the Earth is actually 4.5 billion years old. And the atmosphere would be, 3 billion years at least. So another problem for the old Earth scenario, where the helium balance suggests that the Earth is an awful lot younger than we're told. And again, these are maximum ages. There's the upper limits. You can't go beyond the limit. You can be a lot less. So it's consistent with a young Earth of only thousands of years old. Let's do a bit of history. Enough of science for a while. We'll come back to science in a minute. But to keep everybody happy, we'll do a bit of history as well. We're going to look at the earliest cities and civilizations on this planet. And we're going to look at dragons. Part of history. So, let's think about the oldest cities on this planet. Well, there's two cities that kind of compete for the oldest city in the world. One is in Turkey, Catalhuyuk, or something like that. My pronunciation might well be incorrect. If you're from Turkey, you can correct me. Very interesting place. We visited it a couple of years ago. Here's some photographs of the excavations there. They had a very interesting houses where they didn't bother putting roads between the houses. To go around the town, you would climb up onto the roof and walk across all the roofs. So they didn't have any problems with people hanging around the streets, people hanging around the roofs instead. And conventional archaeologists state that this city is about 8,000 years old. Okay, we might argue a little bit about a few thousand here and there, but not that old. And then look at Jericho in Palestine, which is the other city which claims to be one of the oldest cities in the world. And here we have some pictures of excavations in Palestine. And the conventional archaeologist's story is it's about 9,000 years old. Okay, so these dates, again, are probably maximum dates. And people would argue that the people with a more biblical worldview would argue that these dates could be contracted and made actually to fit in with a biblical timescale. So a good case can be made for a much younger origin of Jericho, definitely, and probably for the city in Turkey as well. But it's interesting to see that these cities are not that old. And let me think about ancient civilizations. There are no civilizations actually older in the conventional archaeological terms, again, than 6,000 years. You've got the Sumerians, which is probably one of the oldest, established in the Tigris and Euphrates area. About 4,000 BC is the conventional age, the generally accepted age. Egyptian history really starts with the earliest dynasties at about 3,000 BC. The Chinese dynasties are actually younger than that. The Shang dynasty in the Henan Valley was about 1,700 BC. And the Mayan civilization, first settlements are reckoned to be about the same time, about 1,800 years BC before Christ. So the question is, if human beings have been around, say, 100,000 years, why did it take so long for them to develop civilizations? There's no good biological reason. If you've got a human being with a brain the size of our brain, evolving, appearing on the planet about 100,000 years ago, in an evolutionary timescale, you would expect them to have developed civilizations before then. But there is no archaeological evidence back further than, even if you're extremely generous to the evolutionary story, about 9,000 years. So the question is, why? Well, the answer would be, for me, well, we've not been around that long. And as soon as there were people on the Earth, they were intelligent like we are. Well, a debatable question maybe. They had a certain amount of intelligence, a certain amount of technology, and they built cities, and they built towns, and they were fairly civilized right from the beginning. And that fits with the young Earth view, and it fits with the biblical chronology. Dragons, one of my favorites. You know, what were the dragons? Were they just myths? Were they just stories that people made up? What was Beowulf up to? Or what was St. George up to? What were they fighting? Was it just stories made up to tell around the fire? Or were they actually fighting real animals? Did these people actually kill the last of the dinosaurs? Because remember, the word dinosaur wasn't invented until 1842 by a gentleman called Richard Owen, who founded the Natural History Museum, I believe, one of the history museums in London. And he coined the term dinosaur to describe these fossils that they were digging up, huge animals, which were unlike anything that we see today. So, before, what were they called? Well, they were probably called dragons. Okay, let's have some evidence. Let's talk about a bit of evidence for dinosaurs actually being around for George and Beowulf and other people like him to go and kill. Well, a gentleman, a German living in Mexico called Waldemar Julsrund, or something like that, discovered some clay and stone figurines, which were dated to a civilization in Mexico which existed from between about 800 and 200 AD. And here are pictures of just some of these figurines. Actually, they discovered about 30,000 different figurines, all made out of clay and stone, every single one of them different, all handcrafted. And Some of them just a few inches long, some of them are actually 3 feet high. And about a third of them appear to be these creatures, dinosaurs. And they've actually been looked at by dinosaur experts, and you can pretty much tie up against known types of dinosaur like Triceratops, Stegosaurus, Diplodocus, even T-Rex, Dimetrodon, and other dinosaur species. So these things are rather bizarre, because if they are actually as old as the archaeologists say they are, 2,000 years old, how did these people manage to construct really reasonably close approximations to dinosaurs if they'd never actually seen a dinosaur walking around? Well, that's a good question. So the one solution is they did actually see dinosaurs wandering around in the Mexican grasslands, and they made pictures of what they saw, because the other figures are of just ordinary everyday things. They're ordinary everyday animals, ordinary everyday objects. But it's not just in Mexico you find these interesting objects, but in Peru there's a variety of Peruvian tomb art from the Nazca era, and they basically, in their tombs, they included ceremonial burial stones with different carvings on them, all sorts of different things. And they had quite an advanced culture. And back in the 1930s, people started collecting these stones, and they started noticing there were some rather funny things on them. This is from a website, www.bible.ca, if you want to look it up. There's quite a lot more information there. And they found stones like this one, which appears to have a man riding on what appears to be a Triceratops. And here we have another one of a guy appearing to be fighting a couple of allosaurs, kind of Jurassic Park. You know, it wasn't all fiction, perhaps. And other stones have animals that look a bit like Diplodocus. The Diplodocus is actually very interesting because I haven't got a picture of it, unfortunately, but according to the text, these had spines on them, which until recently didn't have any support in the scientific literature, until recently when they discovered a skin of Diplodocus fairly well preserved with spines on them. But prior to that period, back in 92, nobody had actually observed these things, yet they were already on these carvings, on these stones, which have been dated to about 700 AD, so about 1,300 years old. So these things are turning up all over the place. And I could go on about petroglyphs in other places in North America, in Australia. But I want to have a look at another interesting one in Cambodia, in Angkor, where there's a very large temple. Is a photograph of their web page, which talks about these interesting artifacts. And here we have a picture of one of the carvings, a glyph it's called, on the temple complex at Angkor Wat. And it looks rather like a stegosaur. And here we have a picture of a stegosaur next to it. And you can see the similarities. It's got the short neck, head down low. We've got the plate-like growths on the back and a short tail. The resemblance is rather startling. And this is carved in a temple which is supposed to be about 800 years old. How do they know what it looked like if they didn't actually see the thing? Because they didn't have the internet. They couldn't go and look at pictures of dinosaurs and say, I like this picture, let's draw one of these. Nobody dug up these fossils. Nobody reconstructed these fossils until the 1800s. So the question is, how did they know what it looked like if they didn't actually see it? Let's come a bit closer to home. Let's go to Carlisle Cathedral. There's a Bishop Bell who's buried in Carlisle Cathedral. He was buried in 1496. And he's got a brass tombstone, or brass tomb plating on the floor. You actually walk over it when you walk up the main aisle, I believe. There's a carpet over it, so you don't damage it. And if you lift the carpet, you find objects carved in the brasswork. And you've got ordinary animals that we recognise today, like a horse, a sheep, dog, a cow. You've got other carvings which are fairly rapidly, very easily recognised from everyday objects you see today. And then there are these two objects. Unfortunately, the photograph isn't so good, so we lose a bit of resolution up here. It's kind of washed out by the flash, which is around here. But I haven't seen them myself, but my father has, and he says they look just like a Diplodocus. Now, to go there, they've got rather annoyed with people wanting to look at this tombstone, and you have to get written permission now from the bishop before you can lift the carpet and have a look at it, because so many creationists have gone there with their cameras trying to take pictures of these things. But they are there at Carlisle Cathedral. And again, the question is, If nobody had dug up a dinosaur until the 1840s or 1800s, early 1800s, and if the term hadn't been invented actually until the 1800s, where did they get the idea to draw these animals on this tomb of this bishop? Well, where did the other animals come from? They were animals that were out there, they could look at and they could see them and they would copy them and put pictures on the tombstone. Why not? And why not include a diplodocus if you happen to have a diplodocus wandering around Carlisle Cathedral? Well, is there another explanation for how these things got there? Personally, I'm very happy with the idea that dinosaurs were actually wandering around Great Britain back in the Middle Ages. And this is why you have the legends of people going out and killing dragons. St. George probably did kill a dragon. He killed a dinosaur. He might well have contributed to wiping out the last species of dinosaur left on this planet. Rather unfortunate from a point of view of species and biodiversity, but there you have it. So I have no problem with that, because that fits exactly what we read in the Bible. If you read the Bible and take it at face value, you find it talks about creatures that can only be dinosaurs. Okay, let's get to the really big one, though. Geology is the big one, because geologists will tell us we can date rocks using radiometric dating, and we can come up with very accurate measures of how old they are, and they come out at billions of years old, and you can't refute that. Well, it's not quite that simple, because there are quite a lot of anomalous radiometric dates out there. And there are also big gaps in the geological column. People tell us, oh, the geological column took so many millions of years to be deposited, and it's kilometers thick, and you've got all these layers, and therefore it must have taken a great deal of time. Well, there are actually gaps. We're going to look at those. We're also going to look at carbon-14 in Carboniferous coal, which, if you know anything about carbon-14 and anything about the Carboniferous, it should be a non-starter. But we'll get there. And we're going to finish off with looking at helium in zircon crystals. So let's look at some radiometric dating. We need to be very careful, because there are lots of assumptions in radiometric dating. You're basically taking radioactive chemicals that break down, radioactive atoms that break down at a known rate with a known half-life. In other words, in one half-life, half of the radioactive compound you have will have broken down to another compound. And something like potassium has a half-life of 1.2 billion years, uranium-238 has a half-life of 4.5 billion years, and something like rubidium has a half-life of actually 48.8 billion years. Now, how you measure that is another question, but I'm not going to argue about that. I'll go with the accepted half-life estimates that are given to us. But the first thing that happens with this is, because the half-life is so long in most of these, it's actually billions of years. If you're going to measure anything, you're going to measure billions of years, because you've got to have a signal that you can actually detect. The minimum age you can detect with these is going to be at least 1 million years or so. And the other thing you need to bear in mind when you're thinking about radiometric dating is that radiometric dates can only be used for igneous or volcanic rock. It can't be used for sedimentary rock, because sedimentary rock's been reworked, so you get no signal out of sedimentary rock. So the only way they can actually work out how old a sedimentary rock is if there's a bit of igneous rock, a bit of volcanic rock in between layers of sedimentary rock. So there are lots of assumptions involved in radiometric dating. So coming from a creation perspective, I think, well, hang on a minute, let's look at these assumptions, let's think about this. Can we be so certain that these radiometric dates are reliable? And you certainly can't date a fossil by using radiometric methods, unless it's a very young fossil, and then you could possibly use carbon-14 on it. So let's think about some of these anomalous radiometric dates. In the literature, there are many occurrences where you get anomalous radiometric dates. And I hope Paul Garner isn't going to talk about this when he comes here. He probably will, actually. So I'm maybe stealing a bit of his thunder, because he's going to talk about the Grand Canyon. Well, this is a cross-section of the Grand Canyon, and we've got two features of the Grand Canyon I want to look at this evening. One is various lava flows in the western Grand Canyon on the Uinkaret plateau, and ancient basalt called a Cardenas basalt, which is in the bottom of the Grand Canyon. So we've got very old and very young on a geological timescale. In fact, the ages that are currently accepted by evolutionary geologists, the lava flow is an age of around 1 million years, so we're told. That's the official age. And the Cardenas basalt has an age of about 1,500 million years, 1.5 billion years. That's the accepted radiometric age of the old igneous rock at the base of the Grand Canyon. Okay, well, let's actually look at a bit more detail at some of the numbers that are produced, because there are different methods different radiometric dating methods that can be used to give you an estimate of the age of these things. So one is rubidium strontium, which gives you an age of 1,240 million years. And there's Sumerian niobidium, which gives you 1,655 million years, and the plus or minus is statistical error. That's fairly accurate within its own system. The lead-lead method gives you 1,883 million years, and the potassium argon gives you 1,205 million years. Okay, you're going to say, well, that's all pretty old. Well, yeah, okay, it's all pretty old, but remember, you've got a limit of detection with your method when you have a very long half-life, and you're always going to come up with big numbers. It's guaranteed. If you get any number at all, it's going to be a big number. But let's actually put these on a chart, put it on a graph. There's 4 different methods down here: rubidium, strontium, Sumerian niobidium, lead, and potassium argon. And what we've actually got are 3 different answers. These are statistically significantly different results. If you apply a standard t-test to these, you can do it yourself. It's very easy to do. It just requires a little bit of statistical knowledge. You come out with statistically significantly different answers. Now, I used to work in an analytical laboratory, and if I had a sample and I came out with 3 different answers, which were all statistically significantly different, my boss would have thrown the method back at me and told me to go away and work on it until I could get the same answer out of 3 samples that supposedly have the same amount of compound in them. The same here. So we're measuring, whatever the answers mean, they're not consistent. They are statistically significantly different. So I don't see why I need to accept this method as being reliable when it can't even give the same answer, or these methods can't give the same answer when applied to the same bit of rock. And it's not just this one bit of rock in the Grand Canyon. It happens over and over again. This is one example of a very old piece of rock where the method doesn't appear to give you a precise answer. So I'm questioning whether the method actually gives you a real answer at all. Then we've got the lava flows I talked about in the Western Grand Canyon. These lava flows are actually very young. They come from the top, young on any time scale, biblical or otherwise. And there were volcanoes up on the Uinkaret plateau in north of Colorado River. And they've produced spectacular frozen lava falls. And geologists consider these lava flows to be Pleistocene age, in other words, only a few million years. Okay, let's look at some of the data again. Actually, it's a bit embarrassing for the geologists because potassium argon gives 1.2 million years. Okay, we're happy with that. But the rubidium strontium gives an answer which is 1,000 times higher, 1,340 million years. So which one's right? Well, we know it's young, so it's going to be the younger one. Okay, so there's an awful lot of these questions are actually unanswered. So obviously, for the geologist, the rubidium strontium age is wrong. But why? You know, if this method has to be explained away over and over again, and it doesn't just happen in a few isolated cases, can we actually trust it? Are we actually going to say, okay, I'm going to accept the geologist's story about the Earth being billions of years old on the basis of radiometric dating when it does appear to be somewhat unreliable? Okay, let's think about the geological column itself. There's a location not far from the Grand Canyon called Frenchman Mountain, which has the same sort of layer of rocks, but it's actually easy to see. If you go to the Grand Canyon, you actually have to walk down an awful long way in an awful hot sun to get to the bottom, whereas the Frenchman Mountain is much easier to see. So why everyone goes to the Grand Canyon is a good question, when you could just go drive up with your car and have a look at these rock layers all laid out nicely by the side of the road. But that's by the by. Apparently the Grand Canyon is worth visiting anyway, so that's what they tell me. But Paul will tell us about that in a couple of weeks' time. But Frenchman Mountain has the same layer of rocks, and there's a couple of places where there's actually gaps. Here I just put up the classic geological column, where you have the Cambrian, the Ordovician, the Silurian, Devonian, Carboniferous, Permian, Triassic, Jurassic, Cretaceous, and Cenozoic eras, going from, on the classic evolutionary time scale, from 500 million up to present day. Well, actually, some of this is missing. In fact, a great deal of it is missing here. You're missing actually a lot of time between the Precambrian and the Cambrian. The Precambrian rock is supposed to be about 1 billion years old, and the Cambrian is 500 million years old. So you're actually missing an awful big chunk of time. It's just not there. There's a gap. There's no rock representing that gap. The only evidence for that gap is a gap. There's nothing, which is actually negative evidence. There's also another gap here between the Devonian and the Cambrian, where you're missing the Ordovician and Silurian, which represents a couple of 100 million years. So the question is, why are there gaps there? Now, that might suggest that the time scale that we're given doesn't always work out, because you have hundreds of millions of years for which there's essentially no evidence. Because we're told that the Devonian is a certain age, we're told that the Cambrian is a certain age, therefore there must be this period of time between the two. But if there's nothing there, where is your evidence for that? Now, to be fair, your evidence, you can find the Ordovician and Silurian rocks elsewhere, but you can't find them in the same sequence. So your time scale is actually not so solid and certain as we're led to believe when you read your geology textbooks. And this great unconformity at the base of the Cambrian actually occurs all around the world, which means you start thinking, what's it mean? Why is it there? And it's in the Frenchman Mountain, the Grand Canyon, but also many other places. And it's a gap of about 1.2 billion years on a geological timescale. But there's evidence for massive erosion, because if there was any rock there, it's all disappeared. And if there wasn't any rock there, it's very interesting because you've got quite a flat layer of rock, and then you've got other sedimentary rock deposited on top of it. So there's evidence of massive erosion. So is this something that happened very quickly, actually, during the biblical flood? The start of a catastrophic worldwide flood will produce this kind of effect in the rocks. And that's rather suggestive that perhaps there's a lot more to the geological story than we're sometimes led to believe, and it actually consistent with having a worldwide flood. Although, again, there's a lot of debate about that. There's lots of discussion that can be had. But, again, these pieces of evidence suggest that the uniformitarian, slow, gradual deposition is not as solid and as certain as we're sometimes led to believe. So, lots of questions here, really, for us to think about. Let's move on to carbon-14. Carbon-14 is not much good, really, when it comes to dating the age of the Earth, because carbon-14 has a very short half-life, as opposed to the other radiometric methods which use isotopes that have very long half-lives. Now, any piece of carbon, you're made up of carbon, by the way, we're a carbon life form, and any piece of carbon of about a gram will contain 5 times 10 to the 12, which is about a billion atoms of radioactive carbon-14. So we're all radioactive, by the way, because we've all got radioactive carbon-14 in us. Fortunately, the radioactivity isn't very powerful, so it's not going to do you any harm, so you needn't worry. Carbon-14 has a half-life of 5,730 years. So when you die, 5,730 years on, you'll have half the carbon-14 you have in you as you have now. Another 5,730 years, you'll have half again. And actually, at about 100,000 years from now, you'll have only about 0.0056% of modern carbon. In other words, that's the terminology they use to say modern carbon is today, but if you go back 100,000 years in the past or in the future, these are all relative, but you end up with, in 100,000 years, you end up with a very, very small percentage because the carbon-14 has decayed as it does. So if you have a sample of material that's got carbon in it, and it's supposed to be 300,000 years old, it will have less than 1 atom of carbon-14 per gram of the carbon. So you take your diamond from your engagement ring, ladies, and you measure you can take the carbon in there, you can measure the carbon-14 in it. I wouldn't recommend it because you won't get your diamond back because they'll destroy it in the process. But you can actually try and analyse it for carbon-14. But of course, nobody's going to do that because we're told diamonds are actually millions of years old. But people have done it. And they started off with coal. Anthracite coal is carboniferous. Carboniferous means that it was laid down 290 to 360 million years ago. So there should be no carbon-14 left in that coal because, as you will know, coal is formed from plant material which is fossilised. So the plant material, when it was killed and buried and turned into coal, would have had carbon-14 in it. 100,000 years on, it would have very, very little carbon-14. 300,000 years further on, essentially zero carbon-14, 1 atom per gram. And now, millions of years later, there should be absolutely no carbon-14. So it's pointless to take a piece of coal and give it to a lab saying, measure the carbon-14 for me, please. The trouble is, people did it. And they come up with some numbers. This is, again, in terms of percentage modern carbon, 0.42% by a team led by a gentleman called Groots, published in 1986. And you can look this up in the literature. It's in the literature. And these numbers are recognised by everybody to be completely bizarre. They shouldn't happen. Because remember we're talking about 200, 300 million year old coal. It should be no carbon-14 at all. So it should be 0, 0, 0, 0. And here we have another one by a group led by Buchan's, 0.3, 0.4 again approximately, and another group published in 1997, 0.2 to 0.35% modern carbon. Now you might say that's not very much. Well, the way you check your method, any analytical method, the way you check your analytical method is you try to measure 0. Right? You take a sample, has nothing in it, and that's your 0. You're always going to get a positive result because of the way of analytical methods work. Now, this method relies on taking a piece of carbon and basically turning it into a gas and firing it through a couple of mass spectrometers. And by firing it through mass spectrometers and applying a magnetic field, they can actually bend the atoms to go different places. And depending on the weight of the atom and the strength of the magnetic field and the speed it's going, you can direct specific atoms to a target and detect them. And that's what they do. So, in theory, this method can be absolutely foolproof and can count one atom of carbon-14. And it can actually filter out any interference. But in practice, of course, you can never do that. So if you do a machine blank, you end up with numbers like 0.08% modern carbon. And other experimenters have checked it out different ways in their systems, and the numbers all come out pretty much the same. About the lowest you get is about 0.015% modern carbon. Small numbers. So what you do if you want to see whether your result is real, you're going to have to deduct that number, the blank, from your reading you get. Now, as you can see, we have here numbers about 0.4, 0.2, and here's your blank. So if you subtract the blank, you still come up with essentially a similar answer. So what we're detecting is carbon-14 in coal that is 300 million years old. How can that be? Well, one answer is the carbon-14 isn't 300 million years old. The coal is not 300 million years old. That, of course, is unacceptable to an evolutionist. But to somebody who believes the Bible, that's perfectly acceptable. And these numbers won't go away. There's lots of debate. You can read all about it on the internet. You can do web searches and come up with all discussion of the pros and cons and the various sources of possible error. But at the end of the day, these numbers do not go away. And they've done it with diamonds too. Diamonds are supposed to be millions of years old, and they find measurable amounts of carbon-14 in diamond. And it's not contamination. They clean them up, and they put the diamond through the process, and you get up with a positive answer in carbon-14. That's impossible. It cannot happen if the diamond is as old as we're told it is. Okay, let's look back to helium. Helium in zircon crystals. Now, the American geologists were looking around, I believe it was in Nevada, somewhere in North America, looking around for rock formations that might be useful for storing radioactive waste. So they were drilling great big holes in the rock down to about 1.5 kilometres and taking out core samples and looking at the rock and see whether it was stable enough to make a good deposit for radioactive materials that they were generating in their nuclear reactors. Still a problem today. But in their core samples, they came up with crystals called zircons, which is basically zirconium and silicon and a bit of oxygen. And it forms nice crystals. Here's a picture of one. They're quite small, most of them, but some of them are quite large enough to see. And zircon is a very interesting sort of semi-precious stone, but it's very common in granite and other igneous rocks. And this is the kind of rock they were actually drilling through in the 1982, I believe they were drilling. And they got to have a lot of rock cores. And zircons are interesting because they're used in radiometric dating with a lead or uranium-lead method because they contain actually lots of uranium trapped inside them. And the radioactive isotopes of uranium, of course, break down, and they break down and produce lead. So zircon is often used in radiometric dating. So what happens is one of the breakdown products from uranium-238, which is a radioactive isotope, is lead-206. And there's various steps in the process. But what happens is you've got 8 steps where you get a helium atom given off. So inside your zircon crystal with uranium impurities in it, you're going to have helium being produced. 8 atoms of helium for the whole process, which supposedly takes billions of years. So if you have a piece of zircon that is billions of years old, you're going to find helium in it. Well, actually, you're not going to find very much helium because helium, being a very light molecule, not attached to the crystal itself, is actually going to diffuse out and get lost. Now, these zircons were dug up, came out of a drill sample, and they were given a radiometric age of 1.5 billion years. the results were published, and what the researchers discovered was that they call it differential helium retention, because they discovered lots of helium in these zircons, which shouldn't have been there because they were so old that all the helium should have leaked out. And this was published by Gentry and his co-workers in 1982 in Geophysical Research Letters. And you can go and look it up. And it's there. It's got all the data and all this helium in the zircons. These are quite small zircons. We'll have a look at in a bit more detail in a minute. Zircon crystals are actually quite small. You only find them under a microscope. So you grind up your rock sample, and you take out the zircons, and you use a microscope to pick them out because they're only 50 to 75 microns in diameter. And there's a photograph of what they would look like. So what they've discovered basically was large amounts of retained helium. In fact, they call them phenomenally large amounts of retained helium because there just shouldn't have been any helium left because the decay rate of uranium is so slow that all the helium would more or less disappear as it was being produced. So the question was, why is this? And this information has been around for 20 years now, 80, 40, 20, 30 years. But some scientists who were interested in the various radiometric dating methods followed up this information and said, okay, there's helium in there. How long would it take for that helium to leave the zircon? Because that will give us an independent measure of the age of the crystals. We've got one measure from the radiometric dating, 1.5 billion years. We can also get a measure from the helium leakage from the crystal. But we need to know how fast the helium comes out of the crystal. And then we can make some assumptions about the ages of these crystals and fit the numbers into the equations and come out with some predictions. And this is what they did. A team led by a guy called Russell Humphreys. They calculated on the basis of the known amounts of helium, and they assumed two ages. They said, let's assume the creation model, 6,000 years, and let's assume the evolutionary model, the 1.5 billion years. And let's plot out the rate of diffusion of helium through these crystals as a function of temperature, because the rate at which the helium comes out depends on temperature. In fact, the crystal's cold enough, the helium won't come out. But if the hotter it is, the faster it's going to come out. So you get actually curves here, which I've shown an example of helium diffusion rate, or diffusivity, against temperature, assuming a certain age to account for the amount of helium you see. And this is the assumption. Let's assume they're 6,000 years old. This is the kind of line you get. Here's the line you get if you assume they're 1.5 billion years old. And that's all very standard methodology. Nothing magic or mysterious here, nothing unconventional, just using conventional maths and physics. And this is what they did. And then they said, well, okay, let's get some zircons and let's actually measure the diffusion rate, the diffusivity of the helium in the zircon, which you can do. Before I move on, just to point out, there's a 100,000-fold difference in the answers you get, depending on whether you take the 6,000 years or the 1.5 billion. So very easy to tell the difference experimentally if you've got a reliable method. And there's no sort of fudging the issue here. So what they did, they got some zircons and they actually did the measurements. They measured the actual rate of diffusion of helium in zircon crystals. And we've got the same graphs here, and here we have the actual experimental data that they recovered when they did the experiment. And it fits the 6,000-year-old crystal theory. I mean, it's absolutely astonishing. For me, it's astonishing. I don't know whether it's astonishing for you, but that is amazing. That is empirical laboratory science, and it with standard methods, and it comes out with an answer which says 6,000 years. So that data is not going to go away either. So from this zircon data, which for me is one of the most exciting pieces of evidence for a young Earth, basically the diffusion rates confirm a numerical prediction based on the reported retentions, what you actually observed in the helium and an assumed young age. So they tested the theory and they got the answer, yes, the theory works. And the measured rates of retention for zircons actually give a helium diffusion age of about 6,000 years, which contradicts by a long way the age of 1.5 billion years based on nuclear decay products from the same zircons using uranium-lead method, which is one of the accepted methods for proving that the Earth is billions of years old. So something is going on here. So basically you've got to make a choice. Am I going to go with one or the other? Or am I going to have to actually reevaluate all the data and all the assertions that the Earth is billions of years old? And to be quite honest, I prefer to say, well, my Bible says one thing, here's some science which supports my Bible, here's some science which doesn't. How do I choose between the two? well, there's no actual objective way to choose between the two. It's up to you to make up your mind. So really, we've looked at lots of different bits of evidence, and I've tried to show you that a lot of this evidence supports the idea that the Earth is young, and I really want to finish up with a short history of the world, as I understand it from the Bible, but also supported by a fair amount of science. So the creation of the Earth is in 6 days, about 6,000 years ago. That's what the Bible says. That's what Genesis 1 says. That's what I believe. And I don't find that I'm actually committing intellectual suicide by doing that, because there's scientific evidence that supports that. And I believe, too, there's a worldwide flood of about 4,500 years ago. Now, we talked about the ancient civilisations. Some of those dates go beyond that, but again, there's a bit of debate about where the dates fit, but the ballpark date is about right. And there would have been a lot of plate tectonic movements after the flood, which is consistent with modern geology, and I don't have any problem with that. All I do is I would say that the time scale is a lot different from what we're told. And one ice age about 100 years after the flood. So there's a lot of information there. And human beings killed the last dinosaurs during the Middle Ages, and dinosaurs and human beings did exist side by side. So that's all I have to say. No doubt there might be a few questions. So Paul's going to come out here and defend me.